So far we have discussed the analysis and performance of single phase transformers. However, majority of the transmission network and power distribution network is 3 phase. Therefore, for to be useful, one should ideally consider 3 phase transformers, which we will introduce today. Now, that should not be a problem if one have a 3 phase 4 wire incoming line. One can use 3 single phase transformers three single phase transformers of the usual construction that we have been so familiar with. And connect them to 3 input lines. In this manner. A, B, C and neutral. Similarly, the secondaries can also be connected in a similar manner. And we will get a 3 phase 4 wire output, which is stepped up or stepped down. So, these 3 single phase transformer together will constitute a 3 phase transformer. This is very much possible, and in many cases this is also done, but something more can be done. Normally, the input voltages will be balanced, that is VAN, VBN and VCN forms a balanced 3 phase system. This is VAN, this is VBN, this is VCN. We know that the flux produced, the magnetizing flux produced in each of these transformer lags the corresponding applied voltage by 90 degree. So, let us call them phi A, phi B and phi C. So, phi A, phi B, phi C are also balanced 3 phase phasors, and we can draw them maintaining same phase relationship. So, phi A will lag phi A n by 90 degree, this will be phi A, phi B will lag phase by 90 degree, and phi C will lag VCN by 90 degree. Just as VAN, phasors VAN, VBN plus VCN equal to 0. Similarly, from geometry, phi A plus phi B plus phi C is also equal to 0. Now, this has some implication, which means the sum of this phasor sum of these three fluxes are identically 0. Hence, instead of putting these secondaries on this arm, if we put the secondaries on the same arm as the primary and merge the three of the remaining arms, the total flux flowing through that arm, that common arm, will be 0, and that common arm can be completely eliminated. Hence, we will arrive at a structure which will look like this. This is the arm for A phase, both primary and secondary. And this merged arm, still the flux produced, this will be phi A, this will be phi B, and this will be phi C, and the sum of this flux which is expected to flow through this merged return path, this will be phi A plus phi B plus phi C, and but this is identically equal to 0. Therefore, this arm is not necessary. Hence, the simple structure would become something like this. With 3 windings, both primary and secondary, here, three arms carrying respectively 3 phase windings. This is for A phase, this is for B phase, this is for C phase. So, this gives a 3 phase transformer as a single unit. Therefore, we saw that we can connect 3 single phase transformers separately to form a 3 phase transformer, or we can build a 3 phase transformer as a single unit. There are advantages and disadvantages of both the approaches, which we will find it, we will see shortly. Before that, let us look at the course structure a little more carefully. The course structure that we had considered so far looks somewhat like this. Ideally, if we assume the core to have infinite permeability, then this Yoke section will have 0 reluctance, and any flux, let us say produced phi A, will divide equally here as phi A by 2 and here through this arm as phi another phi A by 2. Similarly, for the flux produced by other phases. Therefore, what will be the total flux flowing through each of these limbs? So, let us say for the first limb it will be phi A in the upward direction minus phi B by 2 in the downward direction minus phi C by 2 in the downward direction. This is the net flux flowing through limb 1 or limb A. But we have seen phi A plus phi B plus phi C equal to 0, or phi B plus phi C equal to minus phi A. Hence, phi limb will be, limb A will be phi A minus half of minus phi A equal to 3 by 2 phi A. Similar exercise can be done for the other limbs, and we will find that phi limb B will be equal to 3 by 2 phi B and phi limb C will be equal to 3 by 2 phi C. Now, this is a important conclusion, important observation. We find that the flux flowing through the limbs are in fact in phase with the flux produced by the winding on that limb, even when there is mutual coupling between the fluxes. Therefore, the operation of the coils on individual limbs will be independent of each other as long as this relationship, that is the balanced voltage relationship, is maintained. Hence, as far as analysis of a 3-phase transformer goes, each phase can be treated separately, at least with balanced state, applied voltage and in steady state. This makes the analysis of 3-phase transformer very simple. They can be balanced, they can be performed just like single phase transformer, assume if we can find out what is the applied voltage across each winding. Now, this comment should be taken with a caveat, because we have assumed the iron to have infinite permeability. However, in actual practice the iron will not have infinite permeability. In fact, since the transformers are operated very close to their knee point, there will be some amount of reluctance to flux path in the yoke. Therefore, the diffusion of the flux in an actual transformer may not be exactly phi by 2 and phi by 2. There will be more flux flowing through the central limb in this case than the further limb, because this reluctance is higher than this reluctance path. So, the diffusion will not be exactly phi a by 2 and phi a by 2, except for the middle arm where the diffusion will possibly be exactly phi b by 2 and phi b by 2, but for the phase A and phase C the diffusion will not be exact. Hence, this in a practical transformer it will not be completely, each phase will not be completely decoupled, but there will be some amount of coupling, but usually that is negligible. The coupling can be made a little better if we use a different type of core. Incidentally, this is the core type transformer, we call it a 3-limb transformer core. More regarding construction of 3-phase transformer we will see in a later lecture, but to continue with this, this is a 3-limb core which is most commonly used. However, for very large transformer sometimes a 5-limb core is also used. The windings are placed on the inner limbs. While these two limbs do not carry any winding. In this case, we can easily see that the magnetic circuit for each of the phases are more symmetric than the previous case, and hence the assumption of independent operation is more valid in this case. But as we can easily find out that this core is much larger than the core that we have discussed before, hence it is justified only for very large rated transformer. This is called 3-limb core type. This is 5-limb core. There is another construction of the core which is called the shell type construction. Where the central section holds the winding. This also gives for each phase an independent non-interacting flux path. Here also the 3 phases can be treated separately. This is the shell type 3 phase transformer. So, although 3 phase transformer are most commonly found with 3 limb core, some very large transformers are also built with 5 limb core or a shell type core, where the magnetic circuit of phases are either symmetric or they are independent. But as you can see, at least for the shell type core, this is little more than 3 single phase transformers connected together. So, this does not offer the advantages of 3 limb core, it is seldom used. Now, let us look at what are the advantages of using a 3 phase transformer as built as a single unit and 3 single phase transformers. It is the common experience is that if you build a 3 phase transformer as a single unit, then the volume, cost, everything are lower compared to if you build the same transformer with 3 single phase unit. That is a big advantage. However, there are certain advantages of building a 3 phase transformer with 3 single units. For example, for maintenance and reliability purpose, it will be sufficient to keep one spare single phase transformer, so that if there is a fault in one of the transformers, the spare single phase transformer can replace the faulty transformer and the transformer can keep supplying power. However, for a transformer which is built as a single unit, in order to provide redundancy, a full 3 phase transformer is to be kept as standby, which is a more expensive proposition. In certain application, such as in mines, this becomes very important because the space is restricted. Therefore, it is convenient to keep a single phase transformer as a pair, and that is why in mining application a single phase transformer is preferred. There are several other advantages, as we will shortly see, that a single phase transformer, even when one of the transformers develop a fault and is consequently removed, the remaining transformer can keep supplying at least a part of the power, which is not possible with a 3 phase transformer. Also, the maintenance and repair of 3 phase transformer are somewhat more difficult. We have discussed how the core of a 3 phase transformer looks like. Now, let us look at how we can connect the windings of a 3 phase transformer. We have already mentioned that as far as the magnetic circuit is concerned, the windings operate almost independent of each other. So, let us schematically represent the transformer windings. As you can see, even in the simplest of the 3 phase transformer, whether built with a 3 single phase transformer or built as a single unit, there are 6 windings and 12 terminals this can be potentially confusing if we do not follow a specific terminal marking convention, that is labeling convention. Once you are familiar with the drawings and the connections, we can dispense with that, but at least initially it will be useful to follow a certain terminal labeling convention. The convention is very simple. We denote the terminals of the high voltage side with capital letter, for example A2, A1, B2, B1, C2, C1, and the low voltage side with small letters, for example A2, A1. This is capital A2 and this is small a2. The implication is the instantaneous polarities of these two terminals are same. That is, the phasors V A2, A1 indicating the voltage of the terminal A2 with respect to A1 is in phase with the voltage V A2 A1. Similarly, for the other windings. So, following the same logic, V B2 B1 and V B2 B1 are cophasor, V C2 C1 and V C2 C1 are cophasor. Now, what is the simplest connection we can think of? We can connect all 1 terminals together on the high voltage side to form a star point and supply to the 2 terminals A, B, C, in which case the voltage phasors of A2, A1, B2, B1, B2 and C1, C2 form a balanced 3 phase voltage system. This point is N. Now, since these transformers operate independent of each other, the voltages V A2 A1, B2 B1 and C2 C1 will be cophasor to their respective high voltage phase voltages. So, the voltage V A2 A1 will be this, B2 B1 will be this, and C2 C1 will be this. Hence, we can connect the 1 terminals on the low voltage side also in a star and obtain the output voltage on the 2 terminals. That way, the phase voltage and the line voltage on the high voltage side and low voltage side will be cophasor. What will be the relationship between the voltages? Let us see. If the transformer turns ratio is 1:n, then and the line voltage on the high voltage side is VL, then V phase equal to VL by √3 on the high voltage side. This is equal to mod V A2 A1, but we know mod V A2 A1 equal to V A2 A1 by mod V capital A2 capital A1 equal to 1 by n. Therefore, V A2 A1 equal to mod V A2 A1 by n equal to VL by root 3 n. So, the line voltage on the low voltage side VL will be root 3 mod V A2 A1 equal to VL by n. So, the phase voltages and line voltages in this case are related by high voltage phase voltage is to low voltage side phase voltage are related as 1:n, same as the turns ratio. Also, the same relation holds V line of the high voltage side and V line of the low voltage side are also related by 1:n. How about the currents? Let us say the line current on the high voltage side are I capital L and line currents on the low voltage side are I small l. Then if we assume each of these transformer to be ideal, that is the net MMF required to establish the flux is 0, then we can write 1 into IL, since the for this star connection winding current and line current are same, equal to n into I small l. Therefore, IL by I small l is also equal to n:1. Hence, we have for this connection V phase into I phase, which is same as I line, equal to divided by V phase of the low voltage side into line current of the low voltage side, equal to 1 by n into n by 1 equal to 1, or single phase kVA of the both sides are same. Hence, the 3 phase kVA of both sides are also same. Therefore, as we saw that if the transformers are ideal, as in the case of a single phase transformer, the kVA of the two sides of a 3 phase transformer are also same. This connection is called the star star connection or Y-Y connection, and since the phase angle between the line to neutral voltage of both sides are 0, it is also called star star 0 degree connection. Obviously, on the secondary side, had we connected A2, B2 and C2 together to form the neutral point and obtained the supply from the one terminals, then the phase and line voltages should have been in phase opposition to the primary side. This would have been V A1 A2, this would have been V B1 B2, and this would have been V C1 C2. in which case the connection would have still been YY, but now the phase difference between the primary side and the secondary side, or the high voltage side and the low voltage side, would have been 180 degree, and hence this would have been called YY 180 degree connection. Just as the transformer on both sides can be connected in star, they can also be connected in delta. Let us see how the delta connection can be done. As usual, the supply is given to the two terminals, and then we connect A1 with B2, B1 with C2 and C1 with A2. Supply is given to A, B, C. So, taking the voltage VBC as the reference phasor, now B terminal is connected to B2 and C terminals is connected to C2, which in turn is connected to B1. So, VBC is nothing but the voltage VB2 B1, which is shown here, B2 B1, and then terminal A1 is connected to B2 and A2 is connected to C1. This is voltage A1 A2 and this is voltage C1 C2. On the secondary side, these are the terminals A2, B2, C2, and these are the terminals A1, B1, C1. Similar connection is made results in a similar phasor diagram. Please note here also the phase angle between line to neutral is 0. Therefore, this connection can be called delta 0 degree. Had we reversed the connection on the secondary side, that is, instead of connecting A1 to B2, we had connected B1 to A2, C1 to B2 and taken the supplies from A1 B1 C1 instead of A2 B2 C2, then this phasor diagram would have been reversed and we would have got D 180 degree connection. In either case, let us see what will be the voltage and line conversion ratio. Again, we will assume the turns ratio to be 1:n and the line voltage on the high voltage side is VL, line current is IL. On the low voltage side, the line voltage we will take to be VL and the line current to be IL. Here again we find that here for delta connection the winding voltage is same as the line voltage, therefore, we can write VL by VL equal to 1 by N, but winding current is now root 1 by root 3 times the line current, which is at a phase shift of 30 degree compared to the line current. This is phase current. But these two phase currents are also cophasor, and we have I phase into on the high voltage side into 1 equal to I phase on the low voltage side into N, but I phase is I L by root 3 equal to, on the low voltage side this is I small l into N by root 3. Here again we have I L by I small l equal to N is to 1. Hence, the relations for the star star connection and the delta delta connection between the phase voltages, line voltages and phase currents are same. However, this star star delta delta connection has one advantage. Let us assume that we have a delta delta connected transformer sometimes in order to indicate delta connection the windings are placed like this, although physically in a transformer it will not form a triangle, it will be rather what we have shown in this diagram, but this is just a schematic representation. Suppose this was being supplied from a balanced 3 phase 3 wire supply and this was feeding a balanced 3 phase load. Now, assume that this delta delta connected transformer is built with 3 single phase transformers. While operating, let us assume one of the transformer develops some fault and is consequently removed. Then the remaining transformer can still continue to supply some amount of load. When you remove these windings, you get the structure what is known as open delta or V connected transformers. A V connected transformer can continue to supply the load. That is one advantage of using 3 single phase transformer separately to form a 3 phase transformer rather than using a 3 phase transformer as a single unit. Sometimes this is important. Let us see exactly how much kVA or power can be supplied with this open delta connected transformer or V connected transformer through an example. Let us say The line voltage for this transformer was 11 kV, and on this side it was 400 volts, and let us say each of these transformer are rated at 100 kVA. This is made of 3 single phase transformer rated at 100 kVA, and it was supplying a balanced star connected resistive load of 240 kilowatt. Assume the transformers to be ideal. Therefore, if this load was drawing 240 kilowatt, then the input load was also 240 kilowatt. So, what was the line current? LV side line current was this was 346.41 amperes. So, what was the LV side transformer winding current, which was LV side winding current? What was the transformer turns ratio from the given data? The transformer turns ratio was on this side the winding voltage is 11 kV, and on this side the winding voltage is 400 volts. So, turns ratio was 27.5. So, what was the HV side winding current? HV side winding current was 200 ampere by turns ratio . So, 7.273 ampere. This was when it was operating as a 3-phase transformer. Now, let us say one of the transformer develops fault and is removed from the circuit. So, the transformer become a V connected transformer or open delta connected transformer. The question is how much power I can still continue to supply to the load. The constant of course is that the transformer winding current should not exceed its rating while being used as a V connected transformer. So, what is the transformer winding rated current? We have mentioned that each of the transformer is rated at 100 kVA. Therefore, the LV side rated current is transformer winding rated current is 100 kVA divided by 400 volt equal to 250 amperes. So, when you are supplying this transformer with open delta connection, the LV side winding current should not exceed 250 amperes. However, it is easy to see with open V connection the line current on the LV side is same as the phase current, because this winding is not there. This line current flows like this and comes back through this. Similarly for the HV winding, therefore the line current during open delta or V connection should not exceed 250 amperes. What about the phase? It is easy to see that even with open delta or V connection, the line voltages will be balanced. This is so because the supply voltage is balanced, hence the voltage across the remaining two transformers do not change. So, let us say if this was A, this was C, this was B, then this voltage still remains BC, this voltage still remains CA, therefore, this is still BC and CA, and hence this voltage is AB. So, these low voltage side or LV side voltages still forms a balanced three phase system even during open delta connection. So, if the supply is balanced with even with open delta transformer, the LV side line voltages are balanced. Now, if this balanced line voltage supply a balanced three phase load, so the line currents will also be balanced. Hence, with open delta connection we have seen that the transformer will be able to supply a balanced 250 amperes of current. Hence, the total power that it will be able to supply is maximum load kilowatt or load kVA should be equal to root 3 into 400 into 250 amperes, which is about 173.2 kilowatt. Please note that the total rating of these transformers are 300 kilowatt. Total transformer kVA is 300 kVA. Hence, with open delta we can supply approximately 58% of the total transformer kVA. Please note that we have removed one transformer. So, it was expected that we should be able to supply about 2/3 or 67% of the total kVA, but that is not the case. We can supply only 58% of the remaining kVA of the total installed transformer kVA. Thank you.